Hello people, welcome to Just Genius.
Literally just genius.
In this video, we'll be talking about heat transfer. If you didn't hear me properly, we'll be talking about heat and energy, or temperature. First, we have to know the different types of energy. Well, there's chemical energy, electrical energy, radiant energy, sound energy, nuclear energy, gravitational energy, kinetic energy, motion energy, thermal energy, mechanical energy, potential energy, and hydro energy. Mostly, we'll be talking about thermal energy, potential energy, kinetic energy, and chemical energy. First, let's talk about thermal energy. What is thermal energy? Thermal energy is the energy in a substance that is responsible for its temperature. If I had a hot cup of tea, that has a lot of thermal energy. Thermal energy is given off a lot more than you think. Or heat energy is given off a lot more than you think. For example, a light bulb, if I were to use heat energy from that light bulb, I use it, and then if I were to use it to power another light bulb, 90% of the energy is being lost off as heat. Even if I recollect that energy and power another light bulb, eventually there'll be less energy and less energy mathematically. So it wouldn't be possible to do this cycle. There are a few things that can help you measure temperature or measure thermal energy. Temperature is the average kinetic energy a thing has. When something has more thermal energy, it has more kinetic energy, and the particles are moving faster. The more kinetic energy I have, the more thermal energy, the more thermal energy, the more kinetic energy. A thermometer measures the average kinetic energy between the particles, which ends up giving you a temperature scale. Temperature is just the scale, the average scale of kinetic energy. The first scale for measuring temperature was the Fahrenheit scale, which is not really equal. As in our Celsius scale, it's based on properties of water. So, like if you were to calibrate it, which means to give according numbers on a temperature scale that's supposed to react and make them exact. So adding numbers to the thermometer to make it accurate. That's what calibrating means. So if you were to calibrate to a Celsius temperature, well, you dip the thermometer in ice water, and wherever it lands, you would write 0 degrees Celsius. And then you dip it in boiling water at sea level, and then you'd mark it 100 degrees. You'd write 10 different sections between those, and you have your Celsius scale. And in between those sections, you'll add 10 more sections. So you've already calibrated the instrument from 0 to 100. On the other hand, the Kelvin scale is more for sciencey in the lab type of things. It is based on the absolute zero, meaning the unachievable temperature of 0, where no molecules are moving, nothing's moving. It's absolute still. This is not possible, as no one has been able to do it, but with estimation, they figured out what absolute zero was. And absolute zero is negative 273 degrees Celsius. 0 degrees Kelvin is not exactly negative 273. It's actually negative 273.15. But if you were to be asked this on a test or anything, you could just say negative 273 degrees unless specified so. 0 degrees Kelvin in Fahrenheit is about negative 460 in Fahrenheit, 0 degrees Kelvin. It's not exactly that, it's actually negative 459.67, but I just rounded it, so it would be easier to understand. If you don't If you're not understanding when I say scale, I mean a calibrated instrument to show exact measurements of something. In this case, it would be to show exact measurements of temperature, which is average kinetic energy. Most thermometers would contain three things: a sensor, a signal, and a responder. A sensor is a material which is affected by changes in some feature of the environment, such as temperature. So if you were to change it, the sensor would also change. A signal is information about temperature, such as an electrical current. That it's the information that triggers the sensor. A responder is a pointer, light, or mechanism that uses the signal in some way. Like that needs the signal, that uses it. The first person who created some sort of a thermometer was called Galileo Galilei, which was 1564 to 1642. Galileo developed an instrument called a thermoscope. It's similar. Okay, it's a long glass bulb with like a tube. Like, okay, this is the bulb, and there's a long tube. The end of the glass tube is like a bottom. Actually, I'll just show the picture here. When the air in the bulb is cooled, like above in the bulb, when it is cooled, it contracts, and the liquid rises up higher in the tube. When the air is warmed, the air expands and pushes the liquid back down. This is the basic concept of this thermometer that he created. And it's pretty impressive for the time that it was created in. He couldn't call it a thermometer though, because in order for it to be a thermometer, it had to have some sort of a scale in it. This instrument that he created only showed if it was hot or if it was cold in the area. Some people have this still in their homes just for aesthetic reasons. A few of the not the thermometers, but devices that can accurately measure temperature. A few of them are the bimetallic strip, the thermocouple, and infrared thermograms. First, we'll start with the bimetallic strip. It's made of two different types of metals, and they're on both ends of the strip. So it's like a strip, and there's one metal and there's another metal. They expand at different amounts when heated. So their molecules look different when they get heated up. If one expands more, it ends up curving. So if this one was the one expanding more, and this one expands at more temperature, but this one expands at lower temperature, it's still hot, it's still heated, but this one will expand more because it doesn't require that much heat to make it expand, and when it does expand like this, it curves. That's how a bimetallic strip works. These metals can be such as copper and iron, and some people put it in different temperatures, and they mark a certain place to give accurate measurements. Secondly, the thermocouple. It has like a scale, when you're cooking, that type of scale, and with like a hand thing, and then it has two different wires on both sides of the scale. And these wires are also made of two different metals. The two metals are connected at both ends. When a temperature difference between the two ends cause a small electric current to flow through the wires, it will end up resulting in the hand in the middle to like move. One end is called the reference junction, and it's held at a known temperature, like a room temperature, for example. The other end, which is the measuring junction, is to be put in an unknown temperature that you don't know. So if you know the room temperature, you put the reference junction at the room temperature and the unknown junction in, let's say, an ice bath, because you want to measure the ice bath. Then you would see the difference between, and you would know the temperature based on the current. But they need to be calibrated. So you need to find a difference in temperature with both temperatures that you know instead of one that you don't know. And then with the temperature that you know, then you can calibrate the instrument. Finally, let's talk about infrared thermograms. If you haven't heard the term infrared before, I don't know, Bill Nye, Mark Rober, it's because all objects give off infrared radiation, which our eyes cannot actually see. We can only see light, which is a small part of the light. We can only see stuff like this. But that's only a small part of the light spectrum. There's way more than that. And right behind it, there's infrared radiation. We cannot see it, but special types of film and some electronic detectors can. They convert the infrared radiation into colors that can be interpreted as temperature differences. If you were to measure see the exact place on the color scale, maybe you could get exact measurements, but it's just to show if it's hotter or warmer. When I say radiation, I'm like saying given off as light that we cannot exactly see. So it's either vibration or light. It's just a sort of light that we cannot see. It's given off constantly, every day, every second, every minute, every millisecond, but we cannot see it. Now we'll talk about particles, and we'll eventually go to kinetic energy. Some teachers may make you make models, explain it, but particles are a bunch of, two atoms together is a particle. And a bunch of those particles are held together by a force, like a very tiny force. By the way, all matter has space in between their particles. There's no matter that doesn't. So they all have space, even if it's a solid. Even if it's your computer, it has space in between the particles. It's just really small. As the matter changes from state to state, the space between the particles also change. For example, a solid is held together by a very strong attractive force, which all matter has an attractive force. A liquid, on the other hand, is a slight attractive force. It's kind of in the middle. Whereas a gas has like the slightest, almost zero attractive force. Like very little attractive force. It's just everywhere, practically. Literally, it's everywhere because it's right here. When you add thermal energy to matter, the particles, they have more kinetic energy. They're moving faster. You're separating them more. Because, for example, a solid, they're intact. They have a strong attractive force. When you proceed to heat it up, it loosens up and goes to liquid. When you heat it up more, it loosens up, and it turns to hot water, boiling water. When you continue to do this, it turns into steam because it's extremely spread out now. It's basically how it works. So if there's hot air, why do you think hot air balloons, why do they rise? Well, the hot air that's being generated because of the fire's transferring thermal energy to the air because thermal energy always transfers hot stuff from hot stuff to cold stuff. It's transferring the air is now warm. The air is lighter because it has more space in between the particles than the normal temperature air. So the air rises because it's lighter. And while it rises, this is the balloon and this is the air. It rises, and it ends up pushing you up. And the air itself is expanding, so the air balloon ends up expanding and it becomes a balloon shape. From all these energy types, if you haven't noticed a pattern, energy is the ability to do work. Not like energy to clean up your room. More like I need to eat because I need energy, or my lamp needs energy. I need to plug in my computer, it's out of energy. That type of stuff. Expand in the term of temperature practically means the particles are having more space between them. The particles themselves aren't expanding. Just the space between them is expanding, or they're getting more spread out apart. When it contracts, or it like cools down. So the particles, they are more attracted to each other than they were before. Instead of continuing on the fourth topic, expanding and contracting, I'm going to go straight to topic 5 and then come back to that later. Melting. Melting is basically when it's a solid, like for example, ice cubes. If you heat it enough so that it turns from a solid to a liquid, you are melting the ice cube. If you take that liquid that you just melted, or any liquid in general, and you were to freeze it until it became a solid, you are freezing the water. If you were to take that ice cube and heat it to a really high temperature in a short amount of time, and it didn't go to liquid, and it just went straight to gas, which I don't really think would be possible with water. But if it went straight to gas from solid to gas straight away without going to the liquid phase, that is sublimation. If you took the ice cube and instead melted it, boiled it until it became steamy, well, you're practically evaporating it. And in like science terms, in the water cycle, you learned when water evaporates, it goes high up, and that's because the particles, like I said earlier, are not that close to each other, so they're lighter than everything else, and then they can rise up. When these particles in the air, for example, clouds, not trying to bring up the water cycle again, but the clouds, and then when they condense to tiny droplets, the water vapor is collecting together and becoming water again. So it's going from gas to liquid. We're still on the same topic 5. A melting point is a point in which a matter or a specific substance can turn a specific temperature that turns it from a solid to a liquid, that can melt it. Thermal conduction is the transfer of heat between two objects in contact, which they have to be in contact. If two molecules collide, an energy transfer from the hot to the cold molecule occurs. This results in a net flux of heat from the hot body to the cold body, which is again thermal conduction. Heat insulators. Heat insulators are things that stop heat from spreading. For example, we have insulators in our homes, in the walls. This is so that during the winter time, the heat in the house can stay in the house and it doesn't escape. This is in contrast of heat conductors, which are actually meant to transfer the energy and conduct the energy directly. So they do the job faster, while insulators slow down the job. Now, convection. This is the process which heat is transferred by a movement of a heated fluid. When warm air rises in the atmosphere, that is convection. So then, what is convection current? Well, convection current is convection in like a heat-driven cycle that mostly occurs in the air, ocean, and mantle, which is caused by a difference in temperature. For example, if there's warm air and cold air, convection is when they switch places. And then they switch places again. And they keep switching places because the hot air wants to be where the cold air is because there's a difference in temperature. And the cold air, well, he has no choice. He has to go to wherever the hot air was because there can't just be nothing in a place. So there has to be something. So the cold air has to switch too. And then the hot air is here and the cold air is here. And then the hot air wants to go to the cold air. So then they switch. I think you get the point. They keep on switching. This is a convection current. Chemical energy is energy generated by chemicals. For example, glow stick, that is a chemical energy, and it's given off as light, photons, electromagnetic energy. Chemical energy is also in our stomachs. When we eat food, the acid in our stomach, which is a chemical, it breaks it down so we can get the energy. Electrical energy is energy that's electric. Batteries, they have a chemical energy because the chemical reaction is causing the electrical energy. After you take the energy out, first it's potential energy. Then when you take it out, it's chemical energy because the chemicals are reacting, right? Well, they're always reacting. And then after, when they're traveling, it becomes electric energy. Electrons in atoms, that's electric energy. Copper is a really good conductor of electric energy. You use it to power your computers, phones, iPads, lamps, whatever. RSI value measures the insulating ability of matter. The higher the resistance value, the lower the rate of heat transfer through the insulating material. Higher RSI value equals better insulator. Lower RSI value equals bad insulator. Law of conservation of energy, just because it's important, and it's really important in grade 7, heat and energy. It can neither be created nor destroyed. It's the same energy. All energy can be transferred to different states or transferred to different things, but it can never be created nor destroyed. It's always transferring. It's the same energy. All around us is the same type of energy. So it's not going anywhere. It's just circulating. I'm going to leave topic 7 and 8, but I will address the 4 main components of particles or matter, which is space. Space between the particles, attractive force, compelling the particles together so that they don't break around like air, which still has an attractive force, by the way. And P, obviously particles. All matter has particles. And M, it's mass. And also, in order for something to be called or classified as matter, it has to take up space and have mass. So, four main components. All matter has space, particles, attractive force, and mass. Thank you for watching and see you in my next video.